Let's take a look at some optimization problems. So number one, consider the following. We have two numbers, okay, and their difference is 50. Okay, so the difference is 50. And what we want to do is we want to minimize the product. Okay? And what we need to do is write down a couple of equations and then figure out how to use calculus to get the right answer. So the difference between two numbers is 50. Okay, so that's pretty straightforward. We say a minus b, those can be our two numbers, is 50. Now we want to minimize their product. And it's clear that their product is going to be a times b. Okay? So this is what we want to minimize, all right? Now, when you're doing optimization problems in calculus, you're just doing single variable problems. So this is a standard type of problem where we want to minimize a times b, but we don't really know how to do that with two different variables. We do know how to do it if they are one and the same variable. So, as in this problem, we can use the equation above it, a minus b equals 50, to make a substitution into this product equation. Okay? So, if a minus b is 50, it's certainly the case that b equals a minus 50. Just add the b and subtract the 50 to the other side. So b equals a minus 50. You can also say a equals 50 plus b, either way. Now, our product equation, a times b, okay, we could call this a product here, is now going to be, well, if we're putting things here in terms of a, then it's a times a minus 50. Okay, and that is the equation that we want to minimize. It now has one variable, and that is a. Okay, so we take the derivative of this just with respect to a. You can use the product rule here, but it can also be a little easier to actually multiply it out first, right? And so we can say the product equals a squared minus 50a, and now we get p prime of a, or just p prime, equals 2a minus 50. So recall, for an optimization problem, the way you get a minimum or maximum is you take the equation, take the derivative, and then set it equal to 0. So we set this equal to 0, and we solve for this, getting a equals 25. Now what then is b? b is going to be negative 25. And so we have found the two numbers, a and b, that give the minimum product. Now, if you just want to analyze this one quickly, it's a little bit interesting because they're the same number with different signs, but their difference is in fact 50. So one's positive, one's negative. That allows you for the smallest possible number. There is no maximum because you could have like larger and larger numbers whose difference is 50. But if they get super like negative, if they're both negative, it's also going to be a big product. So this does appear to be the correct answer, and it does appear to make sense. It also falls under a group of problems, kind of like if you have a perimeter, to build a fence, how do you maximize the area? And it's going to be a square, like the numbers will be the same. Okay, let us do another one. Okay, so for this number 2, what we're going to do, we're going to find the minimum distance, okay, between the curve y equals the square root of x and a point on the curve, not on the curve, but off the curve. Say and 2, 0. Okay, so how do we do this? Similar type of approach. You could always start these by setting up an equation for what you are minimizing. Okay, and in this problem, you're in fact minimizing distance. So you can always write out the distance formula. Distance is what? Well, it's the difference between y2 minus y1 squared plus x2 minus x1 squared. And now it looks pretty clear because you're given one of the points and you can use y equals root x for the other point. So in this particular case, you can just plug things in. Okay, so let's do that. Okay, so what, y2, well, what is y2? Well, we have, x1, y1, x2, y2. Let's just go with the curve as our x2, y2. So here that's going to be, the y2 would be the square root of x. Okay. Now y1 would be this other point, so it's the 0. And then x2, that's just our x coordinate. And x1 is going to be the 2. Okay, and again, so the idea here is, if you like, this is x1, y1 for us. Wait, is it? Yeah. x1, y1. And then this I'm using as sort of x2, y2. Okay, so it's sort of like y2, x2. But the point is y2 is the square root of x, and it's the only variable, so I'm not going to give it a subscript, I'm just going to call it x. Okay, so this is what we are minimizing. We have an equation with one unknown, which is what you want. Okay, so let's go ahead and take the derivative now. This is with respect to x, we can also write d prime. Now, once again, let me simplify first. Okay, it's always good to simplify these before taking the derivative. When you have something nice and clear, you don't have to, but it's definitely easier because this just evaluates to x. So it becomes x plus x minus 2 squared and all to the 1/2. Now, you might be tempted to multiply out this x minus 2 squared, and you certainly could. I'm not going to, and the reason why is because it's nice to do with the chain rule. Like, it's not hard to take that derivative. I think it's a little more work to multiply it out. Okay, so what's d prime? Okay, so it's going to be all of, the 1/2, right? It all comes down. So it's like power rule. 1/2, so it's 1/2. And then this whole thing in the denominator, x plus x minus 2 squared, all to the negative 1/2, which brings it down, so it's still to the 1/2. And then by the chain rule, we got to multiply by the inside. So what's the inside? It's 1 plus, now we got a double chain rule, the derivative of this piece, that's 2 times x minus 2, and then times the inside, that's just 1, okay? And we've taken the derivative, so to find the minimum or maximum, we set it equal to 0. Now, in the context of these problems, minimum, maximum, if there's only one critical point, you can often assume it is the one that you are looking for. When you are solving problems like this, and you have a fraction, there's a 0, denominator doesn't matter. It's only going to be 0 when the numerator is 0. So what we're solving for here is really, if it's 1 plus, say, 2x minus 4 equals 0. And if we move that over, we get 2x equals 3, or x equals 3/2. Okay? And so that should minimize the distance between the curve and the point. If we want to make a quick sketch, square root of x looks like this. And we're looking at a point, say 2, 0, right here. And then x equals 3/2 is a little behind that. And it does make sense that it should be something like, close to a perpendicular that's going to give you the minimum distance. Okay, let's do one more. Now, optimization problems are known to be tricky. It obviously depends on the problems, and there are a lot of levels. So let's try this one. Okay, for number 3, what if we have the following? We have a circle with a cutout sector, okay, and let's say it has a radius of r. And what we're going to do here, we're going to turn this into a cone, okay, so what would this look like as a cone? Meaning it's like you fold those two sides together and it makes a cone. Okay, so you've got a cone. Let's draw the cone. Okay, here's a nice little cone. Now in this case, R is the side, right? Okay, and what we want to do in this problem, we are going to say find, this can be phrased different ways. It can be find the volume of the maximum cone would be standard. Okay, so find volume maximum cone. Okay, volume here. So, not obvious how to do this, but once again, if you know what you're kind of maximizing, maximum volume, start with that. Okay, so we'll just do the standard sort of equation of a cone. Volume is 1/3 pi r squared h. Now it's important not to mix up your r's, because this capital R is clearly not the radius of the cone, it's the radius of the original circle. So this cone definitely has a separate h and r. Okay, now if we want to minimize or maximize this volume, we want one variable, not two. And this might be confusing to some of you because the capital R looks like a third variable, but in fact, it's given in the problem. What's not given is where you cut it, right? Like what's the angle that you cut it? We're not looking at it in terms of the angle that you cut it, but in terms of the height of the cone and the radius of the cone that you end up with, okay? So we can use this capital R and treat it like a constant. And so what we need here is a second equation, which we have via the Pythagorean theorem. Because h squared plus r squared equals capital R squared. Now, when it comes to making a substitution in this particular case, note that we've got an r squared here and one here. You don't have to say, well, I've got to solve it for h or r. That would be normal, but if, in fact, you need to substitute in for, you want to get rid of one of the variables. If we get rid of r, we can do it more easily by solving for little r squared. So let's do that. So you get little r squared equals big R squared minus h squared. Now we substitute that in. And you get the volume equals 1/3 pi, and instead of h, we've got this r squared h squared, and times h. Okay, only one variable, it's the h. I've always been writing just prime, but if it can be nice to write it too as v of h, and I think I will go ahead and multiply this out. So v of h is, keep the 1/3 pi. The 1/3 pi kind of hangs out as a constant. That's okay, and then we're just focused on the inside, which is r squared h minus h cubed. Okay, so we have our equation now with really one variable h, because r is a constant, and so now we take the derivative and set it equal to 0. So v prime of h equals, leave the constant there, it just comes out. And the first term is going to be r squared, because it's why? Because it's just a constant times h. And if you take a constant times h, like a constant times x, derivative of 3x is 3, it's just r squared, it's just the constant, minus 3h squared. And of course, optimization problem, we want to set it equal to 0. So how does this become 0? Well, it's kind of interesting. The constant doesn't matter because you can divide by it and it's just 0. And so in effect, it's just this middle term that's 0. And so we get that when 3h squared equals r squared. And so we get that h equals, it's the square root of r squared over 3. The square root of r squared is just r. And it's r over root 3. Now some of these problems, well, it's plus or minus, sure, but it's, it's a geometry problem. There's not a negative height. So sometimes you use the interpretation of the problem to simplify it. Okay, so that is h. We have h, and then all that would be left in this problem could be to just find the volume of the maximum cone. And there we've got the h. We don't have the r though, but we do have the r squared. And so we can substitute in for the h squared. So the volume here is going to be 1/3 pi, so r squared is the capital R squared, minus h squared, well, we just square this, that's r squared over 3. And that's all times h, and we just solved that. That's r over the square root of 3. And yeah, we could simplify this a little bit to what? Well, if you could pull out the root 3 down there. 3 over root, what is 3 root 3 as an aside? You know, if we have 1 over 3 root 3, and we try to rationalize this denominator, what do we get? We get root 3 over 9. Okay, so, right, because 3 times 3 is 9. You know, you could do it like that, or you could leave it. The algebra is honestly not that important. I kind of like it as it is, and so basically you end up with pi over 3 root 3, and then we're left with, now these are the same here, okay, because they're both r squareds, right? And so we can actually combine them, okay, except they're going to be in r cubed, and it's 3/3 minus 1/3, so it's 2/3. And the 2, and press simplified again, we'll just say 2/3 r cubed. And we can do a little better, I guess, so let's just, it's a lot of 3's here, but we end up with 2 pi over 9 root 3, right, r cubed. Okay, so that minimizes the, no, it maximizes the cone. Because you can think too sometimes, why is it a minimum and why is it a maximum, not a minimum? We only got one thing. We ignored the negative root. The minimum would be like 0. Yeah, you could have a cone with nothing, and so in effect, it becomes a maximum given the limitation of r, and you can use sort of the little r and little h to actually construct it if you really wanted to.